Alright, so we'll start our discussion on pure rotations, and that's intermediate problem before we solve the problem of fixed axis rotation. So we have to go a little slow on this pure rotation, and we'll just upfront take up an example. So this plane of the board is the XY plane, and the rotation will happen on this plane. So somewhere on the XY plane we have, let's say, an object. I shall just take it as a scale, and then you can fix some point on the scale, away from the scale. Okay, let's for convenience sake take it somewhere on the scale. Now this point is this point of the scale never moves now, so that's the fixed point. Okay, and now imagine that the x-axis is here and the y-axis is here, and the z-axis is passing through this point and it is perpendicular to the plane. So I'm just going to draw it like this, but I think you know what I mean. It's perpendicular to the plane of the board. Now this is going to be the axis of rotation, and please note that this point, let's call it O, never moves. So O never moves. So therefore this is I hope clear enough, an example of pure rotation. So what happens in pure rotation? So first of all, we're going to consider this object. This object is definitely not a particle. That's a big leap now we are making. Okay, this object is not a particle, and this particular rigid body, or the scale, is a collection of particles, but it's a very specific collection in the sense that the distance between the particles remains constant. So that's why it's called a rigid body. So here we go. There are many particles here. Okay, and now what you quickly understand in pure rotation is that these particles, let's call them something, m1, m2, something, these particles are always at the same distance from the origin, and their motion is in the form of circles. Okay, motion in the form of circles. Okay, as the scale moves, the m1, m2 go in circles around the point O. So such motion is called pure rotation, and one quickly notices that in the case of a rigid body, if m1, let's say, rotates by some theta, m2 is also going to be here, m2, and m2 travels a bigger distance in terms of pure distances, but the theta is the same. Okay, so what we will say is d omega, let's just say theta as a function of time is same for all particles. So that's the first obvious observation, and the second observation is that they go in circles. All particles go in a circular motion, but not necessarily uniform. So it could be uniform, of course, but it could also be non-uniform. So that's why in the previous video we discussed the kinematics of such motion. So this is a good example of pure rotation. So what are we trying to predict? So let's try to nail down what is it that we would like to predict. And one important point here is that the scale is acted upon by forces, different forces if you want, external, and this causes, if I could use the word, rotation, or better still, pure rotation. What we would like to tell you is perhaps where is the scale at different times. Well, we know for sure that this point, which is the point of the rotation, the z-axis, doesn't move, so we already know where that point is. But I think what we are trying to predict is what is the angle as a function of time. Okay, so this is going to be the prediction, and it is similar to particle mechanics, where we try to predict what is the position, if it's one-dimensional, as a function of time. Now, given what? So, for example, in the particle mechanics, we were given the forces as a function of time, and we were given the initial position, which we would call x0, 0. Okay, I'm sorry, we can just write it as x0. Let's just call it x0. Okay, or yeah, x0, and then also initial velocity v0. So given x0, v0, and the force history, we predicted x of t. Okay, now let's not go through it again, we've done this before. So here I think, given, very similar, given, I think we also want, we also want to predict the velocity, if it's one-dimensional, velocity in the x direction as a function of time. So I think this is very important. We have to predict both position and velocity. Now, given the initial theta 0, the force history again, okay, on the scale, external force history, and also the initial omega naught. We want to predict theta as a function of time and omega as a function of time. So you can easily relate to my problem by a direct comparison to things that we've already discussed. So there is a clear 1-1 correspondence. So I think there is no confusion. So just want to quickly remind you that here the key role of giving us the answer was force external for a particle is equal to mass into acceleration at any instant of time. Okay, force at any instant of time. And much similar to this, we have a law which is an independent law, which is tau external at any function at any instant of time is equal to some quantity which we will soon meet, some constant which depends on the scale, the shape, and also the axis. Okay, what is the axis? It's the axis is passing through this point and it's perpendicular to the board, into alpha as a function of time. So once again, you notice a clear 1-1 correspondence between the previous problem, and this law will help us to solve this problem. Done. So this is a very specific problem in which the axis is always z-axis and the scale moves in the xy plane. I told you that this is a simple version of the problem, and we'll just stick to it. The plane moves in the xy plane, the axis is z-axis, and it passes through this fixed point of the rotation. Okay, so let's please, again I repeat, we are solving a specific problem, and now I just want to tell you that if I know this, then I think what we've discussed already is how to calculate tau. So let's not distinguish between this and tau. Right. So this is a review of how we were going to solve the problem. But the key question is, what is this? What is this? First of all, so I think we have to have a closer look at this, and where does it come from? So we are not going to call this the law. Rather, in the whole chapter we are going to say there's only one law, which is that tau external at any instant of time is equal to dl by dt, and we've sort of defined system, and therefore also applicable to a particle. Okay, so please note that first of all, the scale is not a particle, it's a system, and I seem to be playing around with simply not put arrows here, and I wonder why. So we'll get back to this in a minute, but this is the law. Okay, one law for the whole set of difficulties we have in this chapter. Now here I have no doubt in my mind that torque is a vector. It's a cross product, and angular momentum is a vector. It's a cross product of two vectors which gives a vector, and this law, like I said, is a law of nature, and we have stumbled upon it with experimentation. What I have to show you, and what I would like to show you, is that the specific problem that we are discussing has this as the formula, is a consequence of the law. Okay, so the law leads, this is a consequence of the main law for the specific problem that we are doing. So I'm going to get to that. So before that, I just want to remind you that, look, I'm going to use this law, but let me not go for an overkill. Let me choose a very simple problem, which is a sub-problem of the main problem. A simple problem, and let's not go beyond this problem, not in 11th and 12th. So the simple problem here is that, and so here's the implicit assumptions to make it simple. The forces are always in a xy plane. So I'm going to make this, please note that I'm not going to go beyond this. Okay, so please note that the forces are always in the xy plane, the force external, and the and also that the axis of rotation is always going to be z-axis in this part of the problem of pure rotation, and in the other problem, which is the fixed axis rotation, the it's going to be parallel to z-axis. So this is going to be highlighted. See, look, it's only because of this reason that this difficult problem becomes much more reasonable. Not that we're going to finish this in a moment. It's going to take us a fair amount of effort to get past even this problem, but it's important for you to realize that things have become easier because of these two assumptions. So let me tell you the consequence of this assumption, and also this, right? uh, the consequence of the first assumption is that, okay, let me repeat again. The consequence of the first assumption that the forces are in the xy plane, and this is what we did now some time ago in one of the previous videos. The torque is going to be now purely in the direction of k. Of course, it can be plus or minus. Okay, it's going to be purely in the direction of k. It will either be something plus k or something minus k. Now, as a result of this, that is why I'm not highlighting this fact that it's a vector. Okay, because it's, well, I think it's better to keep it as a vector because it could still be plus k and minus k. But things are much easier because it's one dimensional now, only in the direction of k or opposite the direction of k, and therefore it's easy to add torques due to various forces. So let's say there are 3 forces and we're going to add the torques, but because I'm doing a simple problem, this addition is not vector addition. It's almost it is scalar addition, and therefore things become much easy. So I want you to keep this in mind. Yes, torque is a vector, but often because we're solving a simpler problem, it'll come down to scalar manipulations and things are definitely looking rosy, right? So because of the first assumption, the calculation of torques on the system is atrociously easy, and we've already done it for all you know. In other words, what I'm trying to say is that if you can calculate the torque due to one force, then you can calculate the torque for every force, and you can just add them like numbers. So here it is. So there is an origin, and then there is this x-axis and y-axis and the z-axis, and we're talking about pure rotation. And now there is this guy, there is a force in the xy plane, and there was a lengthy discussion on how to calculate torque for this force. I think you can so the important point is that the force is in the xy plane, and we've done this calculation. Now if you want, let's say that it okay, it's passing through this point, so we've got r, which happens to be, let's say, xi plus yj, and that's all you need now for calculating the torque. And torque is something in the direction of k, and I think it is fxy minus fyxk, and this could be positive or negative, it doesn't matter. So there you go, this is f1 tau 1. Okay, now you can have multiple forces, f1, f2, f3, and you already learnt it, and therefore you can calculate tau 1, tau 2, tau 3, and you can add them very peacefully because of the fact that they are basically numbers in this simplified example. You just add them, plus minus, and you're done, and you got the torque. So we've already made some progress in the problem. Okay, what is our problem? Our problem is going to come from the one law. There's just going to one law in this whole chapter. In this part of the new things we are learning, there's only one new law. Torque is equal to dl by dt. We seem to know what the torque is. So the torque is, and the torque that we're interested in is only tau z. So I'm going to now stop calling it as a vector and just simply say tau z. Tau z is important in this problem, in our problem. Now look at the next simplification. Okay, and you already realized that tau z is easy, and you can see there's a lot of good news coming in. Now let's look at the other assumption, because we're solving a simplified problem. The axis of rotation is always the z-axis. Okay, so it's always in this fixed pure rotation, it's the z-axis. So now when we try to apply this law to this problem, let's try to write this. So this is tau xi plus tau yg plus tau zk, if you want, is equal to dlx by dt I plus dlx ly by dt j plus dlz by dt k. And now you see that this is not there, this is 0, this is not there, this is 0. Now this automatically means that this doesn't change. Okay, this doesn't change. That is the angular momentum in the component in the x direction is constant. So what we will focus on when doing calculations with this is the only thing that's important. Now this will affect, is directly related to this. Okay, we're seeing the effect of tau z, and that is going to affect only dlz by dt. That's the law. And for example, tau x is related to this and tau y is related to this. Why? Because the I components of the two vectors are equal, the j components of the two vectors are equal, the k components of the two vectors are equal. So we've done this before. If a I plus bj is equal to ci plus dj, then a is equal to c and b is equal to d. We've done this numerous times in this particular course. So what we're trying to say is that if you're doing calculations with tau z, then your focus should be dlz by dt. So really the problem that we're solving is tau z is equal to, which is a scalar number, is equal to dlz by dt. I want to focus on the point that Lz is a scalar. Okay, so please note that angular momentum is a vector, and that is equal to Lxi plus Lyz Lyj plus Lzk, and these are scalars, and we are interested only in this because we are interested in the effect of tau z. There is no other torque component. So the way we will write this is, the law has suddenly become much simpler because we are doing a simpler problem. So the law for us is really in this chapter is dlz by dt. And now I think you must have understood why I left out the arrows on tau and Lz. Really, these are scalars. So long ago I made a comment saying that, look, this is the law for me, and am I making a mistake by not drawing arrows on tau and alpha? Alpha is actually a vector, but for all practical purposes, it's, in our problem, it's a scalar. So finally, in conclusion, I would like to tell you that the law, this is the main law, and someday when you do, maybe you will be working in ISRO or a company that is very important in dynamics, you would be interested in this law. There's little doubt about that. And in this form and in 3D, it is definitely a complicated law. But however, it's not good to do complicated problems up front. So we've chosen a simpler problem to try our luck with this great law of mechanics. And what we're going to dabble around is with problems which uses this tau z, and there's no need for arrows now, is equal to dlz by dt. So now, while it is very obvious that you'll only get tau z because there is an assumption that the forces are in the xy plane. Now when we actually start using this, so this is already done, it's very easy. Our next job in the next video is, how do I calculate angular momentum? And if I calculate the angular momentum of the system, oh my god, I think you have got to remember that we are doing system, okay? That's the important thing. So tau for the system is easy, we're done. Just calculate the torque due to each force, just add them up like numbers. So real big task in front of us is to find the angular momentum. But I'm telling you that, look, let's not do it. Let's just focus on Lz of the system. Let's not worry about L. Okay, you've learnt about L. Okay, great, no problem. And but what we'll do now is immediately go to the simplification. We'll try to see whether we can find Lz of the system. This turns out to be quite nice and easy, and we're done because we're ready to use the law, and it's quite simple. So before that, one more time I would like to tell you, how do I find torque? Well, you know it, but I just want to tell you how to define the problem. How do you find torque, or for that matter angular momentum at any instant of time? I'll tell you what, when is the problem well defined. So for example, if I have a coordinate, so first thing is you got to tell me the coordinate system. If you don't tell the coordinate system, the problem is ill defined. So here is the coordinate system. It is inertial, it's got an origin, it's got the z-axis, and now I tell you, okay, here's the force, okay, and I'm done. So the correct question is, okay, I'll tell you what the force is, and then I'll tell you what is the torque. Okay, so the correct question to ask is, what is the torque about this coordinate system or about O? So really you got to tell me the origin of the coordinate system, and then what I'll do is I'll draw this position vector, and then I'm done. It's R cross F. Okay, so the question can be asked the moment I tell you the origin, because it's a simple matter to find R and F. And the same question, what is L about O? Okay, and then of course you got to tell me where the particle is. So let's say that so one particle, okay, so let's say that the particle is here and it's going in that direction with some velocity mv, and then that's all you need to tell me, because I'm going to draw the position vector. That's at that instant. We are talking about everything is instantaneous, and then I'll do R cross mv. I'm very good at this, okay, at that particular time, and I'm done with the angular momentum at that specific time. So the question has been well posed. The only small change I'm going to make to this program is, look, I'm interested in only tau z. Okay, that's easy because all the forces are supposed to be in the xy plane, and I'm interested only in Lz. Okay, I'm only interested in Lz, and in my next video is completely going to discuss how do I calculate Lz for some problems of interest. No, sorry, in particular pure rotation. And the moment I'll tell you the result beforehand. Lz will turn out to be some constant times omega. So this is the result that will be proved in the next class. Okay, let me write it even better. Lz as a function of time is equal to some constant into omega and that instant. So let me just complete the story. Let's say I managed to prove this. So what have I managed to prove? I think I would like to repeat it one more time. It's easy to find tau z. I'll show that it is easy to find Lz, and it's going to be I omega for pure rotations at that instant of time. Okay, now this is at that instant of time, and now I'll appeal to my law, because that's the only thing I have, and it'll turn out to be enough. The law happens to be that tau z is equal to d Lz by dt. The law says that this is always true at any instant of time, and then I already know tau z, and now you see dLz by dt is equal to I into d omega t by dt, and that is nothing but I alpha at that instant of time, and that is equal to tau, says the law, and this is the law that we are gunning for. So, and that's all that is required to solve the problem of pure rotation. But what I want you to notice is that I need to prove this, right? So in essence, I need to tell you how to find LZ. So if I prove this, I'm done. Okay, one more time, because you might have forgotten the plot. So please remember the problem. There is a scale. Okay, everything is given. The axis is given. This is a quick summary. It just takes 2 minutes to tell you what we're gunning for. I have to predict for you theta as a function of time, and because there is a 1-1 correspondence with problems that we have solved, I have to tell you theta as a function of time. And what I'm given is initial theta, what I'm given is initial omega, what I'm given is the force history, okay, which is the same thing as the torque history. And our experience tells us that you can predict theta as a function of time, you can predict the angular velocity as a function of time, which is because we know that a law like this, which is like F is equal to ma tau z is equal to I alpha, is enough to solve this problem. Okay, what I'm really trying to prove is that tau is equal to I alpha is a consequence of, in this simple problem, it's a direct consequence of tau is equal to dl by dt. System. It's a direct consequence of this for our simple problem, and and the intermediate step is tau z is equal to dlz by dt, and lz is equal to I into omega of time. And what I've been trying to tell you, sorry, it's badly written, but this is the key step. And the moment I manage to prove this, I can do this, and this solves the problem, because we have solved these kind of problems comfortably in the past, so there's no big issue. So we'll get to this main step in the next class, and we are done with a major part of the chapter. Right.